right, so welcome back. So today we'll continue talking about magnetism. So we'll cover the topics of the Hall effect, and then we'll talk about magnetic force on conductors, and then we'll talk about Ampere's law, which is similar to Gauss's law in electricity. So we'll jump in. Um, so for the Hall effect, this is again the application of the magnetic force on charged particles. In this case, you can use the magnetic force, the charged particles, to determine inside a conductor which one is the charge carriers, is either the positive charge or the negative charges. Okay, so the setup looks something like this. So you have a circuit here, and then part of it will be a piece of conductor that you are wanting to find out what would be the either it will be the positive charge carriers or negative charge carrier that's responsible for charge conducting here. So you have this conductor placed in a region of the magnetic fields. So when we have magnetic field and electric field at the same time, a lot of times we things are set up in the three-dimensional. So there's a sign here we use to indicate in the additional dimension, in the third dimension here. So if you have a X, so that means it's pointing in the direction perpendicular to the screen, and then away from you or into the screen in that case. So if you see axis, and then you can imagine this is kind of like an arrow. If the arrow is going away from you, you see X, okay? And then on the other hand, if you are indicating the direction that is pointing towards you, you'll just use a dot or a dot with circle. So sometimes you'll see like X with circle or a dot with circle. So a dot with or without circle, that means it's pointing at you out of the screen in the case. Okay, so in this case, the magnetic field is pointing into the paper. So that's B sub in, that's what it means. Now, um, so if that's the case, now you can measure the voltage on the top and down sides of the conductor. Okay, so depends on the sign of voltage, then you'll figure out if the charge carriers here are positive charges or negative charges. So if these charge carriers are positive because current is going in this direction, so then the positive are moving in this direction. Now use your right hand rule again. So thumb to the direction of the velocity, and then your forefinger goes into the direction of the magnetic field, B field. So your palm is facing up. So that means the electric force on the charges will be moving up, will be pointing upward. So then positive charges will be deflected onto the top plate here. And then as a result, then you'll have negative charge deposit over here. So when you are measuring the voltage across the top and bottom side of the conductor here, as shown up in this case, then if it's positive, that means the charge carriers inside the conductor they are actually positive. On the other hand, so if you measure negative voltages here, then that means they are negative charge carriers here, which most cases is electrons. Okay, so if these are electrons, so again, current goes in this direction, and negative charges are responsible, so the movement of charges will be in that direction, okay, to the left. So again, your thumb goes in the direction of the velocity of the charges, and then your forefinger goes into the paper. Now your palm is facing down, but this is negative charge, so you're flipped. Okay, so again, force will be upward. So now negative charge will be deposited on the top here, and then positive charge will be on the bottom here. So when you measure negative voltage, then you know that it's going to be the charge carriers are going to be negative charges. Okay. So the voltage you measure is equal to electric field across the top and bottom edges of the conductor, and then times the width of the conductor in the case. And the E field will be equal to VD times B, okay? So that's when, again, this is similar to like velocity selector, right? So when you reach to the maximum voltage, so then electric force upward, and then the magnetic force going downward should be equal to each other. So it will then, once you have that, because this is a magnetic force, now electric force will be in the opposite directions, okay? Once you reach that voltage, VH, then it will stop depositing more charges onto the top and bottom edges, okay? So then you get that information again, E equal to V times B, just similar to velocity selectors, okay? Another application of the Hall's effect, if you know your conductor, then you can actually find the strength of the magnetic field, okay? That's the other way around. All right, so moving on to the next section here, magnetic force on conductors, current carrying conductors. So we know that if you have charges moving inside a magnetic field, then there will be magnetic force on the charges. A conductor carries current is basically there are many charges inside the conductor that are moving in the same direction. Okay, so for each of these charges moving inside the presence of magnetic field, then each of them will experience a force, a magnetic force. So then the collective force then will be on the wire, okay, or the conductor, the current carrying wire or conductor. So this will be pretty similar to the magnetic force on charged particles, but in this case now the force is on the conductor or the wire. So then you can also use your right hand rule. In this case, again, you can stay with the right hand rule we had earlier for the magnetic force on the charges. So your thumb goes in the direction of that velocity, and then four fingers go in the direction of the B field, okay? So then your palm is facing up in that case. So, and then you can figure out the direction of the force on the current wire, okay? All right. The magnitude of the force on the current carrying conductor is I times L times B sine theta, okay? So current times the length times B. Current is basically charge times, so this is similar, you don't have to remember this, but when we have force, right, for the charged particles, is QVB sine theta, so oops, let's just go back 1 second. All right, so charge F was QVB sine theta. Okay, so B sine theta, B sine theta, they are the same. So no worries on that. But IL, I is actually Q over T, right? And then times L. So if we do L over T, then that's V. So L over T will be V. So then they are pretty much actually the same thing, okay? Except this is for a single charge, but in here, this is the charge of the current come as a result of those multiple charges, okay? But it's ILB sine theta in that case. All right, so let's take a look on this example here. It says the long thin wire showing the figure is a region of constant magnetic field B. The wire carries current of 6.2 and it's oriented at an angle of 7.5 degrees to the direction of the magnetic field. So the theta in the previous equations, in the equation on the previous page, ILB sine theta, again, this is the angle of the direction of the current and then the magnetic field mix, okay? So in that sense. So it's asking you, A, if the magnetic force is 0.038 newtons per meter, what's the B field? Okay, so we can set this up. F equal to F equals to I LB sine theta. Okay, so we have I, this is I, and then we have the theta. We have, it says force per meter, so that's actually F over L. So that's actually F over L. So then according to the FL over L, it should be I B sine of theta. So then B should be just equal to F over L divided by I times sine of theta. Okay, sine of theta. So F over L is 0.038 newtons over meters divided by I 6.2 amps times sine of 7.5 degrees. Okay, so all this should be in the pair parentheses at the bottom. So that will give us the B field to be 0.047 Tesla. Okay. Next is asking you at what angle will the force exert on the wire per meter be equal to 0.016. So you are now changing the angle and then resulting in a smaller force. Okay. So now you have this B. So B is known. This is the B field. Okay. So again, you'll just use this A there, for part B. You'll use this equation again, F equal to ILB sine theta, but we can do F over L equals to IB sine of theta. Sine of theta. Okay. So now it's looking for the angle. You know this now, you are given that, you have that force, okay? So you just plug in numbers. Now this new number 0.016 newtons equals to the 6.2 times 0.047 sine of theta. And you are solving for your theta. Okay? So divide both sides by these two and then sine inverse. So basically you'll do sine inverse of 0.016 over 6.2 times 0.047. Okay. All right, and that would be 3.15 degrees on that second part. Okay, so first part there and second part. Okay, so let's move on here. So we know that if you have charge carrying wires in the magnetic field, there will be force. Now, if you have a loop, okay, so let's take a look on the loop here. So then each side is a wire. So here, there's a wire here, there's a wire here, there's a wire here and there. So each side will experience a force, all right? So we can use our right-hand rule again. Let's take a look at each side at a time, one side at a time. So on the top side here, this direction goes this thumbs in the direction of the current, and then four fingers in the direction of the B field. So your palm is facing up. So then force here on this guy will be just going upward. Okay, so this is going to be upward, and then let me see if I can just indicate that force there. So on the top here, it's going that way. Okay. Now the same on the bottom here, it's going to be current. The current actually will go in here, right? And then in this direction, and then in the upward direction that way. So current is going on the bottom here, it's going in this direction, which is opposite to the top wire. So then you apply your right hand rule again this way, and then forefinger in the direction of B field, so palm is facing down. So that force on this guy will be just straight for pointing downward, okay, for the magnetic force, F sub B there, and then this guy F sub B on top. Over here on this side here, so thumb goes down in the direction of the current, and then your four fingers will be going in that way direction of the magnetic field. Now your palm is facing towards you, okay, or outer paper. So then we use dot with or without circle. So in this case, there's a circle here. Okay, so it's going into the paper or out of the paper towards you. On this other side, again, current is opposite to each other, so the magnetic force should be in the opposite direction of this guy. If this guy is pointing outward, this will be then pointing downward or inward, okay, to the paper. So one force is out, one is in. So then you'll make this loop rotate, right? But this one and this one will actually cancel on the top here and the bottom here cancel, but then it will just make the loop rotate in that case, okay? So then because of that, there's a net torque inside the coil, okay? All right, so let's now move on there, next page. And then I probably wanted to erase those stuff there. Okay. So the torque in the loop is going to be equal to the force. The force is I L, which is the height of each on the side of the coil, times B. And initially they are starting with 90 degrees, so sine of 90 is 1. So then we don't have a sign here, but times, this is where the force is applied to the x rotation, so it's halfway there, so it's half of the width of that coil there on one side, and then on the other side, the same thing, the same magnitude, the same distance. So those two will add up. Okay, so 1/2 and 1/2 will cancel, and you just have IBHW. Now, height of the coil times the width of coil will be the area of the coil. Okay, so area. So then torque is going to be equal to the current going through times the area times the magnetic field. Okay, and we derive this from the rectangular shape of coil, but it actually applies to any kind of shape. It could be a circular, oval, in irregular shape even, or square, okay? So IA times B in that sense. If your coil and the magnetic field direction, which are not lined up initially, so then there will be a sine theta turn in the torque, okay? Or at a certain point later, these two are no longer lined up, then there's a sign of turn there, sine of theta. Now, this angle theta is the angle, the normal direction of the coil makes with the B direction. Okay, so initially when the coil and the beam, the magnetic field line up, this angle is 90, so sine of 90 is 1. At the time later on, or a different time, if the angle is not 90, then you need to include the sine of 90. Okay. And a lot of times you have many turns of identical coils stack up on top of each other to make a greater torque. So then you'll further multiply IAB sine theta by M to get that total torque, okay, for the coil of N turns. All right. So now moving on to next section here, it talks about magnetic field produced by currents. So we know that if you have currents inside magnetic field, it will actually experience the force. But then on the other hand around, we know that currents produce a magnetic field earlier. So a lot of times you have a current, and then you can figure out, or maybe you have complicated current carrying conductors. Now, what will be the B field that is producing by those currents? Okay, so to determine that, you can use a law called Ampere's law. This is similar to Gauss's law, but slightly different. So this law says the summation of the B field, the magnetic field, parallel to the path. Okay, so in that case, this is how you interpret those signs. To the path over all segments of the closed path is equal to, it's proportional to the current enclosed by that path. Okay, in this case, so if you have two wires, so B field times the tangential direction of that segment, that small segment, and that should equal to, if you sum up through the whole part, closed path here, should equal to a constant number times the current enclosed. And this constant is called the permittivity of free space. If you have everything in vacuum, that's a constant number of 4 pi times 10 to the minus 7 in Tesla times meters over amps. Okay. So let's take a look on the application of that. So the most simplest one is the one single straight wire. Okay. So it carries current. Now, let's say if we are looking for the B field somewhere, a distance R away, okay? So then if we draw a closed path, in this case, a circular, that is the equal distance from the current, okay? So then in this case, the if we take, let's see, if we take a small part here, okay, so B field in this direction, and then we take a small delta L times that times B field. Now let's just erase it for now. Okay, so B field times delta L for a very small portion of this guy. Okay, and then just the sign up through the whole circle. In that case, summation of that. So then for the whole circle here should be 2 pi times R. So it's B times 2 pi times R. Okay. And according to Ampere's law, this should be equal to mu naught times I enclosed. Okay, so I enclosed is this guy. So then my B field, so this should equal to that. So my B field then will be equal to mu naught I over that, which is this guy there. Okay. So this is basically applying Ampere's law to find that. And then that should be in Tesla's, okay, for the magnetic field there. All right. And for the direction of the B field here, now this is called right-hand rule number 2. Again, your thumb points in the direction of the current. Now your forefingers should curl in the direction of your B field. So in this case, then B field will be in this direction, which is like this here, okay, in this direction, and then going in this direction there. So kind of counterclockwise if you look from the top side down, okay, for this. All right, let's take a look on this example here. It says find the magnetic field 7.25 centimeters away from a long straight wire carries current of 6.81. Okay, so this is basically just plugging the numbers of the magnetic field for a current carrying wire should be mu naught times I over 2 pi R. Okay, so you just plug in your numbers there. Mu naught is 4 pi times 10 to the minus 7. Okay, and then I is 6.81 divided by 2 pi times R. That's in centimeters, so you need to convert that into meters first. Okay, make sure you have everything in SI unit. So at the end, you'll get 1.88 Tesla of magnetic field out of this current carrying wire at 7.25 centimeters away from it. Okay. All right. And then we will take a look on another example here. So this one says two long wires, straight wires orientate perpendicular to the page. Okay, so one is carrying the current out of paper, representing with the dot here, and then the other one is carrying current into the paper, representing this cross. So it's asking you find the magnitude and direction of the magnetic field at point P, where's here. Okay, so This wire will produce a magnetic field at point P, and then this wire will produce another also magnetic field at point P. So then the total magnetic field at point P will just add up. Okay. In that case, now magnetic field, it's a vector. So if you have two of them add up, then that means you need to do vector additions. Okay. So let's take a look on this one here. Let me just switch over here because I need a little bit more space for this problem. Okay. All right. So as I mentioned, there. Let's determine the direction of the B field by these two first. Okay. So for this guy pointing out of paper, so some points out of paper towards you, your four fingers curls in the direction of the B field. So then B field by this guy, by this one, this over here should be in the direction, okay. So this will be a B field in that direction. This is number 2, so let's say that's 2. The other one, by I1, it's pointing into, so then you curve it in this direction, okay? So in that case, this is gonna to be in this direction here, okay? B of 1, okay? So B1 and B2 will add up, okay? Now, this should be a right angle here because it should be perpendicular to the radial direction. It should be in the tangential direction. Okay, so magnetic field produced by a current carrying wire should be in the tangential direction. Okay, and then this guy, this B1, it's perpendicular to this here. Okay, so they are not in the same line in that case. Okay. All right, so let's find out maybe the magnitudes of the two first. Okay, so let's see. Oh, wait, a little bit up there. So magnitude of B1, we can do B1 magnitude first. B1 should be mu naught I, right, over mu naught I1 over 2 pi R1. Okay, so this guy is R1. This guy then is R2. Okay, so 4 pi 10 to the minus 7 times I1 is 3.0 amps over 2 pi R1 is just the side of this square. Okay, so it's indicate like 5 centimeter there. So times 5 centimeter, that means 10 to the minus 2. Okay, so that magnitude of B1 is equal to, let me see, 1.2 10 to the second Tesla. Okay. Now for B1, we can do similarly, or B2, sorry. For B2 is mu naught I2 over mu naught I2 over 2 pi R2. Okay. So again, 4 pi 10 to the minus 7. Now I2 is 4.0 amps over 2 pi times the diagonal of a square, which would be square root of the side. Okay, so times square root of the 5 times 10 to the minus 2. Okay, so we'll get about, let me see, B1, B2 in this case, I think I have a weird number, but I'll just write it down anyways, 0.5 or 0.8, okay, times square root of 2, and then times 10 to the second Tesla. Okay, so point A is 4 over 5, point A is 4 over 5, and then this 4 pi and 2 pi cancels, becomes 2. 2 over square root of 2 is square root of 2. Okay, and then 10 to the minus 2 will flip up, or it will, yeah, can partially cancel that out. And then becomes 10 to the, hold on 1 second. Yeah, actually it's going to be times 10 to the minus 7 here. I'm forgetting about that. So this on top here will become not to the 2, but so it's minus 5 here. Yeah, minus 5 because I'm forgetting 10 to the minus 7. So minus 5 on top there. Okay. All right. So let's see. Now, B1 is just in the X direction. Okay, so all B1 is in X. B1 will not have Y. Okay, B2 here. So let's take a look on the angle here. So this is diagonal direction here, and then this is perpendicular to that guy. So, and then this one is 45. Okay, so then that means this one is also 45. Okay, but here horizontal to this vertical is 90, so this part here will be 45 as well. Okay, so there's 45 there, and then there's 45 here, there's 45 there. Okay, so then for the B2 x, B2 of x, it's going to be equal to, it's 45 there, so it's cosine. So it's B2 cosine, but minus is pointing in the minus direction, minus a B2 cosine of 45 degrees. So you basically do 0.8 times square root 2 times 10 to the minus 5 times cosine of 45 degrees. Okay, so that's the x direction, and then that's a negative sign in front. So this will give you minus 8.0 times 10 to the minus 6 Tesla. Okay, in the x direction. In the y direction, okay, so B2 of y will be the same. Just it's pointing down. Oh, actually, it's pointing downward. So that is minus B2 again. Now this time will be sine of 45 degrees. Okay, we know sine and cosine of 45, they are the same. So this will be also minus 8.0, 10 to the minus 5 Tesla. Okay. So now the total B of total x should be B1 x plus B2 x. So B1 x is everything of B1, so it's 1.2. Let me see. Oh, this is minus 6. Sorry, not minus 5. So minus 6. Let me see if I can erase that. Okay. 10 to the minus 6. Okay. B1 everything, it's top there. So 1.2 times 10 to the minus 5. So that means 12 times 10 to the minus 6. Okay, so we can do 12 times 10 to the minus 6 and plus B2x, which is minus 8 times 10 to the minus 6. Okay, so we will have 4 times 10 to the minus 6. That's not on that. And then on the y, and the y will be just coming from B2, right? So B of y, and then will be just coming from B2y, which is minus 8 times 10 to the minus 6 Tesla, okay? So x and y. Then we can do the total, which will be square root of x squared plus y squared. So square root of that 4.0 times 10 to the minus 6 square plus minus 8.0 times 10 to the minus 6 and square. Okay, square root that together. So then at the end you'll get 8.9 10 to the minus 6 Tesla. Okay, for the total magnetic field. magnitude, and then it's a vector, so we want to know also its direction. Okay, so theta of it should be tangent inverse of the y over x. Okay, so -8 over x is 4, and then 10 to the -6 and 10 to the -6 will cancel. Okay, so doesn't matter. So this will give you minus of 63 degrees. So that means it's totally it will be pointing downward, minus of 63 from the positive horizontal direction. Okay. All right. So going back to the slide. All right, so let's summarize what we learned today. We talk about Hall's effect. You can use it to determine the direction or the sign of the charge carriers in the conductor. And we talked about the magnetic force on current carrying wires because charges in the magnetic field experience force. So then current carrying wires is collective of charges that moving in the same direction inside the wire. So the wire will collectively experience magnetic force due to force on each charge. We also talk about Ampere's law. That's a law tells you how you can calculate the B field due to a current carrying wire. Okay, and then application of that for a straight wire will give you B field by a straight wire to be mu naught I 2 pi times R. R is the how far you are away from the wire, and then mu naught is the constant number of 4 pi times 10 to the minus 7. Okay. All right, we'll stop here today, and then we'll come back next time. Okay. See you guys.